Good afternoon to everybody who decided to take part in today's Sano seminar. Well, as it was last time, we organized this in a kind of hybrid way. So a part of Sano team is on the third floor of Sano venue. And of course, as usual, we have a number of participants attending the seminar remotely. Today, as a speaker, we have Marek Wodziński, who is a senior researcher at Sano, and at the same time, he is assistant professor at the IGH University of Krakow. And Marek works in a biomedical area, and he has a quite outstanding experience working not only in Poland, but he spent a lot of quite number of time of working at Hessau Valley in Switzerland, and his research was recognized by many awards. One of the most important award was the journal Politica Scientific Award. And he now at Sano has become a leader of a project, and he will probably today will give overview of this project. And he already has team with one PhD student and one postdoctoral researcher. So, as usual, we will have a lecture, and during this lecture, if you have a question which is necessary to be asked, because this will facilitate understanding the talk, please ask this question on chat or on questions and answer, and I will try to transfer it. And of course, as usual, after the talk, we will have a part of the seminar devoted to discussion and to question and answers. So, Marek, now both floor and screen is yours.
Okay, thank you for this kind introduction. Today I would like to show you our goals of the MultiGeoMed project funded by the NCN Sonata 20 program, entitled Unifying Voxels, Meshes, Point Clouds, and Implicit Models. I would like to show you the general overview of the project and our plans for the next months. So, the goal of the project is to unify at the same time, simultaneously, several different geometric representations. Currently, in medical imaging, usually we use one chosen representation at the same time. For example, voxel grid for segmentation, for example, point clouds for shape reconstruction, sometimes implicit models for neural rendering, and many other applications. However, there are quite little works presenting simultaneously, using simultaneously several different presentations at the same time to utilize the strong sides of each of them and also to discard the limitations. Before I start the description of our plans for the project, I would like to just quickly remind you what kind of representations we have, what are their strong sides, and also what are the limitations. So I'm pretty sure that majority of you are familiar mostly with voxel grids. Voxel grids are very commonly used in medical imaging. I would say they are the most widely used representation in medical imaging because they have quite important pros. I mean, they are very well structured, they are very easy to process, and they also provide you the full field of view. However, in terms of the geometric learning, there are several limitations of this kind of data. Firstly, they are not dedicated to process sparse data. For the sparse data, you need to use a dedicated approach. For example, the Minkowski engine or others, which are not trivial to use and also have their own limitations. Moreover, it's very difficult to process high resolution volumes. Basically, you cannot process high resolution volumes without using patch-based approach, which is not, which is not useful in many real applications when you need actually to have this full field of view. Moreover, voxel grids, they are not really resistant to resolution changes. They are very often very prone actually to resolution changes. So you need to choose particular physical size of the voxel during the training. And also by design, they do not learn geometric features. They are mostly dedicated to learn textural features, and that are not the best idea to use when processing shapes, not textures. Apart from voxel grids, we also have point clouds. Point clouds are very widely used in computer vision, not that common in actually medical imaging. And point clouds, they have also quite important strong sides, like the fact that they are very efficient. They are dedicated directly to sparse structures. You don't need that much memory, both during training and inference. They are unstructured, so they are easy to split and also to merge. They provide you by design the full field of view for particular shape, and they are resolution agnostic. However, one of the properties that are positive also is at the same time is a quite significant limitation. Because of the fact that they are unstructured, the connectivity in point clouds is not preserved, which is crucial for numerous applications. Moreover, point clouds, they are noisy, and it's very difficult to capture fine details when using point clouds. Then we also have surface meshes, and surface meshes, they are quite unique because they show you only the surface of particular structure. But they provide you directly the connectivity of particular organ, particular structure, which is very beneficial for a lot of downstream tasks. Moreover, this is the representation that is desired by majority of the downstream applications, for example, for the 3D printing. And also similarly to point clouds, they are resolution agnostic. So it's much better representation for geometric deep learning compared to voxel grids. Also the limitations of surface meshes, they exist. Actually, the connectivity of surface meshes is only captured locally because tracking the global connectivity is very computationally ineffective. So you can only capture the local connectivity using surface meshes. And also, unfortunately, they are computationally intensive and they do not scale well with the number of vertices and edges. And then the fourth representation that we are going to explore in this project is the implicit representations. They are quite, I would say, new. This is quite a new kind of geometric representations because people started to work on implicit neural fields representations, I think, in 2015, more or less. So it's 10 years old compared to voxel grids, point clouds, or meshes. It's much younger representation. And in this representation, the shape is directly saved as a neural network in the features of in the weights basically of the neural networks. And after the conversion, this representation is very easy to process, is very effective. It also provides you the full field of view for particular shape, and is also resolution agnostic, similarly to point clouds and to surface meshes. However, the limitations of these representations are also quite significant because they require they require a method, actually learning-based method, to convert the shapes to the implicit representation and also from the implicit representation. They are not intuitive to process. You cannot directly visualize the structures in this representation. It's basically just a huge, big black box that you cannot easily interpret. And also it requires fine-tuning particular neural network to each instance of particular shape separately, that makes the processing problematic and not that easy as with the other representations. In this project, in the MultiGeoMed, our goal is to propose deep learning models that are going to use all these representations simultaneously to improve several different downstream tasks in medical imaging, starting from, for example, shape reconstruction, going through volume segmentation, reconstruction, and also to the image registration. We also, the primary goal is to utilize the strong sides of each modality while discarding the limitations of them. Our main research objectives in these projects are as follows. So firstly, at the end of the project, we would like to propose a foundation model that is dedicated to medical shape reconstruction using 4 geometrical representations at the same time. It's our PhD student Wojtek PhD thesis. Then we will also develop, unify, and make available as open source a dataset consisting of more than 100,000 medical shapes, safe at the same time with using all these 4 aforementioned geometrical representations. Also in 2028, we would like to organize an open scientific challenge and dedicated to multimodal medical shape reconstruction. Basically, we plan to release the data set to organize a challenge where everybody can join and compete to propose the best method to reconstruct medical shapes. And what's quite noteworthy, please remember that this particular project, it's funded by the National Science Center under the Sonata program. So it's dedicated to basic science. So in this particular project, the main outcome are basically publications. We plan at the end of the project to have at least 10 conference or journal articles presenting the outcome of this work. In terms of the research team, we finally completed our small but I hope effective group. So the team consists of 3 people. It's me as, let's say, the coordinator of this research. We also have Wojtek that joined us in October. He's a PhD student at Sano and at AGH University of Krakow. His main research topic in this project is the medical shape reconstruction, the multimodal medical shape reconstruction. He is going to explore how to unify these different representations to perform as much effective as possible in terms of reconstructing medical shapes. And then we also have Gniewos that who joined us in February, so just a fresh member of the team. And he is going to work on medical image registration, medical image classification, segmentation, using different geometric representations simultaneously at the same time. All of us are going to also to be responsible for collecting the data that we are going to use in this project. And also we are going to together we are going to organize the challenge during hopefully MICAI 28 in Brazil. Even though the project, I would say, just started, we already have the website. So if you are interested in the progress of the project, the website will be updated, I think, quite frequently, every month or so, where all the updates about our research outcomes, about the data set release, about the publications is going to be posted. So all the information about the progress is going to be there. So please, if you are interested, you can easily follow this website. In terms of the pipeline of the project is planned for 3 years. Officially, it started in October 2025, so we are already 4 months, 5 months actually, inside of this project. We started from basically implementing library for multimodal geometrical deep learning that is in progress. We also started with acquiring medical shapes that can be processed in our downstream tasks. And now, since Gniewosz started, we also started officially and practically our three initial work packages. And the initial work packages, they are dedicated to unimodal geometric deep learning. So we are going to propose several different methods working separately using point clouds, separately surface meshes, and also implicit representations. In these work packages, we are going to work on reconstruction, segmentation, classification, and registration. Yeah, and then after the first, basically after the half of the project, after the first year of the project, we are going to start the main work package of this research. So the work package 6, and the work package 6 is going to be devoted to the multimodal, the multi-representational geometric deep learning, where we are going to propose method that simultaneously use these three geometric representations to solve particular downstream task. Of course, during the whole project, we have also the work package dedicated to acquire and harmonize the data sets. This work package is currently in progress, so we are actively working on that. We are basically acquiring as many volumes and shapes as possible. In terms of the current status of this project, in terms of the data, actually, we have currently acquired, preprocessed, and unified almost 5,000 medical shapes, presenting different structures. For example, aorta, for example, pelvic, the pulmonary artery tree, kidneys, circle of Willis, and also many others, so that we have already prepared for our downstream task. So this is work in progress. In terms of the data, we are currently working only on 3 representations. We are working on the voxel grids, surface meshes, and point clouds. And the reason is that we are not using yet implicit representations, because before we will be able to use implicit representations, we need to propose a method that actually is, I would say, a foundation model dedicated to saving templates for implicit neural fields. And this is our initial research that we are doing. We are proposing foundation model, meta-learned foundation model, that will be able to quickly adapt to every single instance, every single shape separately. We have explored several different meta-learning schemes, for example, a reptile. And we have shown that actually it's possible to use meta-learning to dramatically increase the speed of memorizing the shapes using implicit neural fields. By meta-learning, for example, here you can see that by using reptile initialization, basically after just 400 iterations of fine-tuning the model, we are going to basically completely reconstruct particular shape with a dice score close to 1. And for example, it allows us to basically tune particular model to a particular shape in just about 100 milliseconds for the perfect fit. Which is a very nice result, and this will allow us to basically process the 4th modality in real time. But this is still work in progress. We plan to release the foundation model, the compression foundation model, very, very soon. In terms of the next steps for the data, our plan is to acquire, preprocess, and unify at least 25,000 shapes before the end of this year. So basically, with this number of shapes, we can start to propose, at least to work on the foundation model dedicated to shape analysis. And we plan to have, before the end of this year, to have this implicit model dedicated to saving the implicit representation ready before the end of this year. And also before the end of 27, our plan is to acquire and then also release at least 100,000 medical shapes that are going to be released openly in a scientific journal, for example, Scientific Data or similar. The goal to acquire and release this at least 100,000 shapes is the plan, I would say, minimum. I think it's possible that we will acquire and release a data set with even more than 1 million shapes. So this will be quite huge data set for all applications of shape analysis. In terms of the reconstruction, shape reconstruction is the Wojtek's PhD research topic. And here, just to make this clear, what does it mean for reconstruct a medical shape? The goal is that you have basically a medical shape that is just partial, that have some defect. Here, particularly, this particular defect is because of some mechanical damage, but the defect may be, the source of the defect may be quite different. For example, it may be also for example, low resolution, for example, of CT scan, and the same the model because, for example, of low CT dose delivered to the patient. For example, it can be also just a very simple thing that, for example, the field of view that was acquired was not perfect. Or, for example, you can simply have some occlusion for 2D data in computer vision that you would like to somehow solve and somehow recover the missing part of the volume. So all these downstream tasks, they can be considered as shape reconstruction, and that's one of them, I would say, the most important research problems in this project. And actually, in this project, our main research question that we would like to answer is how to propose reconstruction model that actually generalizes well to previously unseen medical shapes. And because, it's not problematic to propose a model that, for example, reconstructs skulls, for example, or different bones or some soft tissues when it was trained on huge data set of such shapes. This problem is already known how to solve this. The question that we would like to solve is how to actually reconstruct shapes that the model has never seen before. For example, suppose that we are training the model on, for example, pelvic bones, for example, skulls, for example, aortas, kidneys, etc. And we would like to, for example, generalize into liver that was never existing in the training database. And that's the main research problem that you would like to propose to make this model, I would say, organ or structure agnostic. But however, this is the problem that we are going to solve in the next 3 years during the whole project. In terms of the current status of the reconstruction, Wojtek has already prepared baselines, a whole, I would say, pipeline of using NNUNet for the voxel grid-based reconstruction. For each data set separately, also for all and chosen combinations for these data sets. This will serve as our, I would say, the most, I would say the most primitive model to perform the reconstruction. It's far from being the ideal solution to shape reconstruction. However, still, that's the main state of the art in medical shape segmentation. And that is very similar actually to reconstruction. And in the voxel grid domain, reconstruction actually is a segmentation. So we are going to use this model as our baseline. And everything here is already prepared. And the next steps that we are going to explore in the reconstructions are to firstly propose a whole framework to generate heterogeneous synthetic defects that can be used for training reconstruction models and that actually generalizes very well. So we plan to train using synthetic data, but our models are going to generalize into real medical defects, real medical damages. And also at the same time, Wojtek is going to work on the reconstruction models that are going to use point clouds and surface mesh representations. To the end of this year, we plan to propose, I would say, initial foundation models dedicated to medical shape reconstructions using these two modalities, so point clouds and surface meshes. Then our second topic that we are currently exploring is topology preserving segmentation. And this is the main research topic of our postdoctoral researcher, Gniewosz. And here the goal is to propose methods that utilize multimodal geometric deep learning to preserve the connectivity of tubular shapes. The research problem here is as follows. I mean, how we can actually ensure connectivity with very small structures. For example, when you have the diameter of just one voxel. In terms of the current models, firstly, it's very difficult to even evaluate these kind of algorithms because the die-score, for example, Hausdorff distance, these metrics are useless in verifying the correctness of this kind of segmentation. We need to use different ways how to assess the quality of such segmentation. And our research question that we would like to ask is, how can we improve the solution to this problem, how we can solve this problem by using different representations simultaneously. Because actually our intuition is that by using, for example, simultaneously voxel grids, because the CT, for example, or MRI images, the textures, they are stored in voxel grids. However, our intuition is that by using simultaneously, for example, surface meshes at the same time, it may improve the connectivity of such small structures because these representations, they directly enforce the connectivity. So by simultaneously, for example, creating mesh and voxel grid, it may be useful to improve the connectivity of the final segmentation results. And also we plan to eventually we plan to evaluate all of this using the fluid dynamics, fluid simulations to see how for example, blood flow is preserved in the segmented structures. We are not going to based on the purely, I would say, quantitative measures like die-score or Hausdorff distance, because as I mentioned, they are not useful in this context. And here we have already also prepared the baselines for the tubular shapes segmentations using NNUnit, and also a pipeline to automatically evaluate the topology-rated metrics, such as Betty numbers, center line agreement, and also the connectivity of the segmentation outputs. And our next step, after having these baselines that are going to serve as our, let's say, the comparison that we are going to compare against, our goal is to firstly explore how to jointly use voxel grids and surface meshes to enforce the tubular shapes connectivity. How to enforce the center line, I mean, how to basically stabilize the center lines of the segmentations, so we can correctly segment even the smallest branches of vessel trees. But eventually, at the very end, we would like to combine all 4 geometric representations simultaneously to enforce the tubular shape connectivity during the image segmentation. Because here in this particular context, also implicit representations, they may be very useful for this task. Because of the properties of the latent space that we can utilize. And also point clouds, they may be very useful because they provide global field of view that actually for high resolution volumes, this may be quite problematic to actually segment directly from the voxel grid to maintain, to maintain the connectivity. In terms of our publications plans of this project, we plan to release our first results, first conference publications in late 2026. The first publications will be related to unimodal shape reconstruction and also to multi-representation segmentation of tubular shapes. That's our initial plan for this year. However, the main scientific outcomes of this project, they will be related to the publications releasing the foundation models dedicated both to medical shape reconstruction, but also to multimodal segmentation and registration. But the foundation model, because of the complexity of this task, they are going to be released at earliest in 27, 28, when we are going to close this research project. Apart from this foundation model publications, we also plan to release a publication describing the dataset in 2027, together with all the associated software, and also a publication describing the reconstruction challenge outcomes that we are going to plan to organize during MICAI 2028. And since, as I mentioned before, this is National Science Center funded project, it focuses mostly on publications, on basically the knowledge creation, knowledge sharing. So here, the outcome of these projects are scientific publications. And in total, in this project, we plan to release at least 10 to 15 open publications presenting all the methods, all the deep learning models, all the training pipelines that we plan to propose, evaluate, and describe during the project. And yeah, I think that's it in terms of the introduction to the project. I hope that next time, after the first year of our work, we will already have some concrete results that we can share and describe, and also first publications that you can check, that you can read, and also the data that we can openly share with everybody. If you have any questions about the project, you can of course ask them now, but also don't hesitate to ask me to contact me using my Sano email, and also stay tuned for all news on the website, on the project website. And we are really planning to start to basically to upload all the materials, all the news quite frequently. So this website will be up to date in the upcoming maps. Thank you for your time, and if you have any questions, please ask.
Well, many thanks for your talk. And well, we have already a question from Olaf. Olaf, please go on with your question.
Hello. Yeah, actually, I have two questions. So the first is, of course, well, how, even if this is a, let's say, basic research project, do you see direct connects to things that have already been worked on in Sano? For example, I know that there are some people who have done 3D shapes for tooth and those things. And the second question, more important, of course, there is MedShapeNet, and this already has 100,000 structures. And they also have a foundation model. Admittedly, is their definition of multimodal really that they just take point cloud plus text? But text was not included in your multimodal description. So how do you relate? Are you a direct competitor, or is it orthogonal, or how do you see that?
Okay, so in terms of the first question about other topics in Sana, about this, I'm pretty sure that yeah, there are many people working on basically on geometric deep learning. I'm aware of these models. I believe about that tooth segmentation. I'm not fully. I mean, I'm not sure about the details, but I don't think they used multimodal, but maybe I'm wrong. But of course, I mean, this particular research is very connected, very strongly connected to other research teams at Sano, and hopefully other teams can benefit from the knowledge that we are going to create here. In terms of the MedShapeNet, I would not say that this is that we are competitive to MedShapeNet, because MedShapeNet, they are not, up to my knowledge, working on multimodal geometric deep learning. They are working on rather unimodal geometric deep learning. Of course, they have collected already quite huge database of shapes. However, quite a lot of these shapes there, they are not directly useful in, for example, shape reconstruction or others, because a lot of the structures they are very noisy. They are not very well, I would, preserved in terms of the data quality. But of course, actually, we plan actually in this particular project, we also plan to utilize part of the MedShapeNet database, because indeed part of the database is created very, very nicely and can be directly used for our purposes as well. In terms of the foundation model of MedShapeNet, I have tested this foundation model, and unfortunately, it does not generalize at all to previously unseen shapes. So I think there is still quite a lot of work to do to basically to make this model stronger and better. However, still, it's very nice model because it's very nice proof of concept in terms of what can be done. Because for the distributions that the model have already seen, it's very nice, I would say, shape language model, quite novel thing. But here in this particular project, we are not planning to cover the language part of this thing. Actually, for that we plan to submit another grant proposal, and that it will be directly dedicated to a more applied science, because we believe that this is not basic science anymore. This is rather applied science when you want to actually solve particular downstream task. But yeah, in terms of the MedShapeNet, we in the future we actually are going to compare also about against the model proposed there, and we are also going to use the data in this data set. And I think that I'm pretty sure that in the future we may also create some kind of collaboration together. But still, our goals, I believe, are quite different.
Thank you.
Thank you very much. Well, we have a question from Maciek Malawski. Maciek, please go on.
Okay, thank you for this nice overview. So I have a question about this generalization, yeah, for the unseen types of shape, because this seems to be quite a challenge in these models. So could you share with us some, the way how do you are going to approach this problem to generalize these tasks into really this kind of shapes that were not seen, or maybe there is some some catch that there is only a class of objects or class of shapes, or how are you going to approach this task?
Actually, the thing is that in terms of generalizing to previously unseen models, this is very similar to human. I mean, we as humans, when we see particular thing for the first time, actually we don't know whether this particular thing is complete or maybe it's defective. So we as humans, we cannot actually work with the things that we have never seen before. So our strategy actually to handle previously missing shapes, missing types of data, is to make the models, the foundation models, very easy to tune during the inference. So our goal is to propose model. Our first idea is to use meta learning for that. Models that can be very easily adapted to particular self-supervised task during the inference. And by using something like that, we can actually fine-tune our model during inference to every single case, even to case that we have never seen before. So the model can basically analyze this particular shape for a given self-supervised downstream task. And then we can basically utilize the latent space that, thanks to meta learning, will be, I would say, much more smooth to generalize the knowledge into different downstream task that actually requires, for example, annotations, like, for example, shape reconstruction. And this is something that we actually need to verify. The idea is not verified yet. We need to think about it. We need to implement that. And we need to evaluate that. But I'm pretty sure that this, I would say, zero-shot learning can be actually combined with meta learning, can be actually used to generalize knowledge to previously unseen cases.
This is very very interesting. I see that when we are looking in general into this deep learning models, they are indeed trying to generalize and try to find these analogies. So if we look at this problem of some missing fragments of shapes, or this kind of challenges, we could think of generalizing this or finding analogies between tasks.
I think basically that here the problem is how to teach the model to learn fast. So the problem is how to make the model able to be very quickly adapted to different downstream tasks. And that's something that is very, very, very often ignored when working with current models. Of course, I mean, the whole current very popular technique. I mean, popular field of research about foundation model is about that, how to propose models that can be very easily actually adapted to previously unseen downstream tasks, to previously unseen data. But still, I think that people are mostly, right now at least, focusing on foundation model, but proposing very big models, so models that are trained on huge amount of data with huge resources. But here we would like to actually propose foundation models that are oriented into a bit different thing. So foundation models that have latent spaces that can be very easily adapted, can be very easily fine-tuned. And that's something we would like to explore here.
Yeah, thank you. Sounds like an interesting plan.
Many thanks. And well, now we have Janek Fischer in the queue. Janku, please go on.
Hello. Hi, everyone.
Hello.
First, I have a question about what you answered now. So I think the idea is very valid, but have you ever seen any other domains? Because I think it's a general approach that could be applied to any domain of deep learning, of a downstream task. So have you ever seen this approach for other domains?
Yeah, Fred, there are initial works in computer vision about making models easy to fine-tune by meta learning. So that's something that already, I would say, people started to work on that. But apart from computer vision and the similar topics, I think that the most important research area where this kind of problem is very strongly rated is reinforcement learning for robotics. Because robots they need to adapt to very different tasks very easily. So the main work about meta learning trained foundation models they are currently in robotic reinforcement learning.
And also there you see, like, have you seen the like retraining during inference, or that's how you call meta learning?
No, I mean retraining during inference is a bit different thing than meta learning. Meta learning is I would say the process of training a model that is able to very quickly
I agree.
adapt to new tasks. So that's the first side of this problem. Fine-tuning during inference is called instance optimization, where we basically optimize a particular model for particular instance of the data. This can be also I think, called zero-shot learning. And this is very widely used currently in practice in many domains. But the problem is that currently in the instance optimization, it is very difficult first in terms of the computational complexity, for example, in image registration. But also the problem is that the instance optimization currently it is not using parallelly different downstream tasks. So they are not using at the same time features for self-supervised learning and, for example, for supervised heads. So it's very difficult to fine-tune models using self-supervised learning that automatically generalizes to downstream task supervised heads. So that's something that we actually need to explore in this project.
Okay, thank you very much. And another question of mine is actually I agree with that. Dice especially is problematic, especially for the little structures. So I didn't catch if you got into any valuable alternative there. You were describing this one project with this problem.
You are asking about the tubular shape segmentation, yeah? I mean,
yes. About a valid metric for little structures, little target segmentation, and so on.
So I don't think that there is one single metric that can be used to evaluate correctly the tubular shape segmentation, that's for sure. So we will need to report several different metrics simultaneously. And of course, even DICE or Hausdorff, they will be some kind of supporting metrics that may be useful. But I think that the most important evaluation metrics will be changes in Betty numbers, will be the number of connected components in the center lines after the segmentation, But I think the most important actually evaluation metric for this kind of tasks will be the simulation of the fluid flow. So to compare how the fluid flows in the ground truth and how the fluid flows in the segmented structure. I think that will be the most important and most, I would say, universal and reliable evaluation way of these methods.
Okay, all from me, thanks.
Thank you very much for discussion. Well, all this question and discussion was with online participants. I think that there may be some questions or comments from the third Sano floor.
I can maybe add something about those metrics because actually my name is Dnieposz, because I don't know if anyone knows me already. So maybe I can add something about this, metrics that, as Marek said, there is no one metrics, but many people about connectivity use called connective dice or CL dice, which is also not like one good metrics that we should only use this one, and probably like as Marek said, I prepared some pipeline that actually describes the output with many metrics, and I don't know if there is like better way to try to maybe merge into like some one joint metrics. I think that those separate metrics sometimes say a little about different things about the connection, but as I also seen in publication, people rather publish many metrics that one current or something.
And actually, for example, centerline dice can be also used to regularize the models during training. So this can be also used as some kind of improving the segmentation outcomes. However, in this particular project, we directly want to utilize the multimodal multi-representation training because I mean, surface meshes by design, they are connected. So by utilizing by design the connectivity, it should be much easier to actually make the segmentation reliable without the necessity to, for example, fine-tune the relative hyperparameters for the centerline dice or different regularization parameters that are dedicated to preserving the topology during segmentation. I don't see more questions from the audience on the third floor, so I think
yes, and but anyhow, I think that one issue which was mentioned during the discussion was about computational complexity. I think that this is also important issue in comparison of these different approaches. Yes, where besides of memory complexity, it is also something what should be taken into account.
Yeah, I mean, definitely. Currently, in terms of the medical shape reconstruction, just to make this clear, I'm not speaking about the general shape reconstruction, but about concretely medical shape reconstruction. People mostly focus on the voxel grid presentation.
Yes.
And this is, from the computational complexity, it's a disaster. Because for the medical, for example, shape reconstruction analysis, we would like to capture the very fine details of the shapes. And for that, we need to have very high resolution of the volumes. And for everybody that, for example, processed high resolution CTs or MRIs, everybody knows that we cannot process this kind of data on the fly, I mean, and without dividing into patches. We need to divide them into patches. But for the geometric deep learning, dividing into patches is another disaster, because then we lose the global features of particular shapes. So actually, we can't directly just process the volumes patch in the patch-based manner. So we need to propose another alternative, and this is quite sad. But because of the fact that all the volumes or almost all the volumes in medical imaging comes from CT, MRI, also ultrasonography, they are inherently volumetric data. They are voxel grids. And the amount of works, for example, using point clouds, surface meshes to process this kind of data is very limited. In computer vision, where the data comes from different sources, when, for example, you have these depth maps or different source of point clouds, for example, then it's different story. But in medical imaging, this area in general is not explored very well. And in
Yes.
my opinion, we are very strongly devoted to actually capturing the fine details, because the fine details are the most important things when processing medical shapes.
Many thanks. Well, I don't see more questions online, so I think that it's time to thank our speaker. Marku, many thanks for your talk, and congratulations on obtaining such ambitious grant anyhow. And well, I hope that it will be a very successful development of this research. So
Yeah,
many
I also
thanks.
hope that we will manage to actually deliver all the things promised. But we will see in the upcoming months, upcoming years, what will be the final outcome of this project.
Yes, it's research. It is not a pipeline production. So it's of course,
The success is never gone.
I think that having in mind, the discussion which we had, it seems that it will be also something what would be interesting for many colleagues in Sano. So I think that it will be also a kind of way of collaboration between different teams. So
yeah, I
so
mean,
it's great.
We are very open to any kind of collaboration. So if you see here any topics that basically are of mutual interest with your research, then don't be scared of us. I mean, just comment. We can talk, because we are very actually open for any kind of collaborations with others. Also within Sano and also outside of Sano. So if you are actually outside of Sano and you would like to cooperate with us, please write to me. We are very happy to collaborate. And also thanks for the invitation for this seminar. Hopefully next year we will have already some concrete results that we can present and share it with the audience. Thanks.
Thank you very much. Well, I think that one of the way to get more external collaboration would be to present somehow this project at this VPH 2026 conference in Milano. They have extended the deadline for presenting abstracts until next Monday. So maybe
we'll check that. Yeah.
Will be possible to somehow to present this project in such a way that abstract will be accepted. So anyhow, many thanks. And well, I would like to invite all of you to seminar in a week from now. It will be seminar on something which is known under acronym VVUQ. So you will see abstract soon and invitation. So thank you very much, and see you in a week from now. Right.
Thank you. Bye-bye.
Bye.